Recording again. Okay. So, okay, let's continue with the IMC based design. Are you guys with me? Arkadaşlar geldiniz mi? Tabii gelenler var, gelmeyenler de vardır herhalde, bilmiyorum. Okay, so the idea is that we will base our controller on the stable zeros of the estimated plant. Okay, so we have those unstable zeros, but we will not consider them in the design. We will assume again, basic idea is that derive the controller based only on the stable zeros. Let's erase the S. On the stable zeros of the plant. Okay, we will also assume a certain first order overall response. Again, actually a first and sometimes higher. I will comment on that in a minute. Overall response. For the time being, with a time constant tau c, which is a design parameter. We assume that the overall overall response with a time constant tau c. We further assume a model controller in the form. Now this is not a derivation, it's actually a definition. So we make an assumption in the assumed controller. Okay, so I'm putting this as a definition. It will be 1 over GP minus, that means the inverse of the plant excluding the unstable zeros of the plant, so that this reciprocal function does not have any unstable poles, times 1 over 1 plus tau cs to the power r, where r is equal to 1, 2, etc. Okay. By the way, guys, I forgot to mention that this derivation, you can find it. Let me put it over here. Okay. So internal model control, you can also read about this discussion in Chao's book. Okay. PC Chao, which is one of our references. Okay. Process control, a first course in MATLAB. There is a chapter or a section on this topic, and it also goes over all these derivations. Okay. Now this power R, okay, higher powers are considered to make the controller realizable. Okay, so I'm not going to go into too much of a detail here, because that's going to distract us and it's going to make things much more complicated. But you can see here what's happening. If you increase R, you are actually increasing the denominator order of the controller. So that has an effect to cancel the order of whatever is in the numerator in 1 over GP. So if GP is a high order system and with a lot of terms in the denominator, which is often the case, okay, you will have much more terms in the denominator rather than the numerator, okay. So 1 over GP minus will have a lot of terms in the numerator. So GC star may end up, and in fact later on GC may end up to be non-causal. So you often may consider increasing R in order to make the resulting controller a causal controller, okay? But that's really not to be too much. Let's not focus on that for now, okay? So let's remember this. We will use this in a minute, okay? Let's call this star, okay? So now what we will do, by the way, this is not an arbitrary proposal, okay? I mean, it looks arbitrary here, but note, okay, the above controller form can be, in fact, derived if you assume, in fact, GP tilde is equal to GP and disturbance is equal to 0. So if you make that assumption that GP tilde is equivalent to the plant and you don't have any disturbance, in fact you can derive this, you can derive GC star from the given plant transfer function, okay? And obviously desired T is equal to 1 over tau CS plus 1, which is a first order overall transfer function. So you can do that if you want to, okay? Now we will combine everything that we learned with the Padé approximation. So let us combine all this with an FOP dt plant. So with a specific plant using also Padé approximation, so that we have a specific approximation for the plant transfer function, okay? So now assume that we have a model GP tilde, and the model is first order plus dead time, okay? So e to the minus theta p s over tau p s plus 1. Sorry about that. Sometimes I use theta d, sometimes I use theta p, but what I mean is basically the plant time delay, okay? Now using first order Padé approximation, using first order Padé approximation, basically this plant transfer function is given by GP tilde is equal to the this already first order part and what's coming from Padé approximation, 1 minus theta p over 2 s 1 plus theta p over 2 s, okay? Okay, so let's merge that together, okay? Now GP tilde obviously has this unstable 0. So we will basically use GP minus, okay? GP tilde minus with the only getting rid of the unstable 0, we basically have another plant model that is tau p s plus 1 and theta p over 2s plus 1. Okay? And obviously gp plus, which we will not use, is equal to this remaining unstable. Okay. All right. Let us choose r is equal to 1 and see what happens. In star to give us GC star expression, which is going to be tau ps plus 1 times theta p over 2s plus 1 over kp times 1 over tau 1 plus tau cs. Okay? So we have an expression for GC star. Now let us also use, remember, we are not after GC star because all we want is an output feedback based controller in the end. So what we will do is that we will transform this GC star into its equivalent in an output feedback architecture. Okay, now let us use our expression, which is which we had derived before, where GC is equal to GC star over 1 minus GC star and GP tilde. Now I have GP tilde and I have GC star from here. Okay, and GP basically I'm going to use this, right? This is going to go here for this model over here, and for GC star, okay, I'm going to use the above derived formula. So the rest will be just simply manipulating all the polynomials and hopefully we will arrive at our result. Okay, so let me try to do that for you. Okay, it's going to be quite I hope I don't make any mistakes and you guys will correct me if I do. Okay, so I have GC, which is my controller transfer function. In the numerator I have GC star, so I'm going to write that here, tau p times s plus 1 over theta p over 2 s plus 1 divided by kp times 1 plus tau cs over 1 minus, right? If I multiply the 2, okay, in the denominator I will have 1 minus theta p over 2 s over 1 plus tau c times s. Okay, because GC star GP multiplied has some cancellations in it. Okay, so that's going to be 1 over kp from the numerator. Okay, and then you know, these terms will cancel out at the denominator, so I will have tau p, numerator and denominator will cancel out. So I will have in the numerator I will have the terms from over here, okay, theta p over 2s plus 1, and in the denominator 1 multiplied by 1 plus tau cs, so I will have 1 plus tau cs minus 1 plus tau theta p over 2s. These two terms cancel out, okay, and if I expand the numerator I will get a second order polynomial, tau p theta p over 2s squared plus if I regroup the two terms, tau p plus theta p over 2s plus 1, and in the denominator I will have kp tau c plus theta p over 2 s. So let's make the division. So I will have tau p theta p over 2 over kp tau c plus theta p over 2 times s, okay, plus again tau p plus theta p over 2 divided by the same denominator, tau c plus theta p over 2, and here s's cancel out, so I don't have any s term, plus 1 over kp tau c plus theta p over 2 times 1 over s. So we can already see that we have a PID controller, but what I want to do is also rearrange it in such a way that we clearly define the PID controller terms as well. Okay, so this is clearly, you see, this is the constant term. So what I'm going to do is I will put it into this parenthesis, theta p over 2, and I have also a 1 over kp term here, kp. Okay, so in the denominator I have tau c plus theta p over 2 s, sorry, what s? No s here, theta p over 2. And inside, if we want a dependent ideal PID, what we should have is 1 plus 1 over tau I times 1 over s, and plus tau d times s. Okay, so what I need to do is to also find, this is clearly our kc already. Okay, now find tau I and tau d. Okay, so these are the terms that when multiplied by kc will give us the terms that we have in the above expression. Okay, so let me write that down. We have 1 over tau I being equal to simply 1 over kp tau c plus theta p over 2 times kp tau c plus theta p over 2 over tau p plus theta p over 2. So we have these terms cancelling out, which is giving you 1 over tau p plus theta p over 2, which gives you your tau I. Okay, so your tau I is tau p plus theta p over 2. Okay. Also, as our final step, tau d is similarly, we can find it directly, over 2 over again kp tau c plus theta p over 2 times kp tau c plus theta p over 2 and tau p plus theta p over 2. These terms cancel out, so you get also 1 over 2 terms. Okay, so we can write it like this, 1 over 2 times tau p theta p over 1 over 2 times 2 tau p plus theta p. Okay, 1 over 2's cancel out, and your tau d turns out to be tau p theta p over 2 tau p plus theta p. Now the reason I spent this time to do all the calculations is that now compare these, okay, compare these results with the PID controller parameters in the IMC PID table. Okay, you will see that we have obtained those results. The final line where we had the PID controller design formulas, in fact, are equivalent to what we have derived here. Okay. All right. Any questions so far? So that really concludes our PID discussion and the derivation of the IMC-based design formulas. We will move on to a new topic. Okay? Any questions so far? Arkadaşlar, soru var mı? Okay. So,
hocam benim bir sorum var sana. Bu IMC'de bir tane bizim aslında olan bir plant modelimiz vardı ya, bizim kendi yazmadığımız. Onun etkisini böyle bir şekilde görmedik burada. Ya da gördüysek bir şey mi esüm ettik? Ben onu tam anlayamadım.
Ben de sorunuzu tam anlayamadım ama şimdi şöyle, bizim şimdi bu modelde şöyle bir varsayım yaptık. Tekrar şu diyagrama geliyorum. Şimdi burada şöyle bir varsayım yaptık. Şu gerçek plant modeli unknown kabul edildi. Ve istedik ki GP'yi hiçbir yerde kullanmayalım. Ama neyi kullanalım? GP'nin bir approximation'ın elimizde olduğunu varsayalım ve ona da explicitly başka bir isim verdik. Ona GP tilde dedik. Ve yaptığımız her şeyde GP tilde'yi kullandık. GP'yi kullanmadık.
Peki yani bunu nasıl becerdik hocam? Yani GP sonuçta bu sistemin içinde var ve bir şekilde elimizde formüllerimizde çıkmadı. Nasıl oldu? Ben o kısım kafam karıştı.
Şöyle çıkmadı. Biz burada bu IMC architecture'ında şunu dedik. Ve aslında her şeyi ona göre formüle ettik. Dedik ki GP tilde aslında GP'nin bir approximation'ı. Ve dolayısıyla ideal durumda GP tilde GP'ye eşit. Bütün varsayımlar onun üzerine kurulu. Yani GP tilde'nin GP'nin bir approximation'ı olması üzerine dayalı. Ve elimizde olduğunu biliyoruz GP tilde'nin. GP ise elimizde değil. Şunu unutmayın arkadaşlar. Bizim buradaki amacımız sistemi simüle etmek değil. Bizim buradaki amacımız şu. Sistem hakkındaki bildiklerimizi kullanarak GC star'ı bulmak. Arkasından da mümkünse GC'yi bulmak. Yani şunu bulmak. Sonuçta bulduğunuz şey sizin hesaplarınız sonucunda bir controller elde ediyorsunuz. Bu controller gerçekte kullanılırken GP tilde falan olmayacak. GC'yi GP'ye bağlayacaksınız ve çalıştıracaksınız. Aradaki fark bu. Şurada bir model var. Biz bu modeli sadece controller'ı derive etmek için kullanıyoruz. Controller için bir takım formüller geliştirmek için kullanıyoruz. Ama geliştirdiğiniz controller'ı fiziksel olarak kullanmaya geldiğinizde siz GC star'ı ve arkasından elde ettiğiniz GC'yi cebinize koyacaksınız. Götüreceksiniz, plant'e bağlayacaksınız ve çalıştıracaksınız. Eğer GP tilde makul bir model değilse ve elde ettiğimiz formüller anlamlı formüller değilse, o zaman siz bunu götürüp de GP tilde üzerinden derive etmenize rağmen götürüp GP'ye bağladığınızda makul bir performans elde etmeyi umuyorsunuz. Bilmiyorum, cevap oldu mu?
Anladım hocam.
Yani GP'yi biz hiçbir yerde kullanmadık tasarımda. Sadece GP tilda'yı kullandık. Ama elde ettiğimiz kontrolleri götürüp aslında GP bile değil, unutmayın GP de matematiksel bir model. Her şey burada matematiksel bir model. Gerçekteki plant hiçbiri olmayabilir. Çünkü lineer bir modeli olmayabilir. Hiç modellenmemiş etkiler olabilir içinde. Dolayısıyla gerçek plant bambaşka bir canavar olabilir yani. Sonuçta siz plant ile ilgili bir takım varsayımlar yapıyorsunuz. Bir matematiksel model elde ediyorsunuz. O matematiksel modeli bile ideal kabul ediyorsunuz. Burada GP. Ona da bir yaklaşık bir model buluyorsunuz. GP tilde. Bunu kullanarak bir controller elde ediyorsunuz. Sonra götürüp o controller'ı gerçek sisteme bağlıyorsunuz. O noktada tabii ki bir gerçek performans elde ediyorsunuz. Önümüzdeki dönem 406 dersinde şöyle şeyler göreceksiniz. Sistem nonlineer ama siz o nonlineer sistemi Simulink simüle edeceksiniz ve gerçekten de sistem elinizde olacak. Sistem olacak, sistemin nonlineer modeli olacak Simülink'te. Sonra ama siz şey yapacaksınız. Bu nonlineer modele belli bir ekilibrium etrafında bir lineer model approximate edeceksiniz. Bu lineer modeli kullanarak bir controller elde edeceksiniz. Elde ettiğiniz controller'ı götürüp hem gerçek sisteme hem de sistemin nonlinear modeline bağlayarak deneyler yapacaksınız. O zaman sistemin lineer modelini assume etmenin etkilerini göreceksiniz yani. Controller'ı elde etmek için lineer bir model assume etmenin. Bilmiyorum, çerçeveyi çiziyor mu?
Çiziyor hocam, teşekkürler.
Başka soru var mı arkadaşlar? All right. So, in that case, let me start our new topic. It's going to be an introduction for today. Tomorrow we will continue with this. Okay? Let's save this and open a new. Now, this is essentially lumped parameter versus distributed parameter, systems. Okay, and I'm gonna put out a couple of my note pages for you to remember the lumped parameter version because we will now study the heat conduction in a solid body, and this is taken from Fikar's book, so you can also go ahead and take a look at Fikar's discussion of this topic. This is a distributed parameter system, a distributed parameter system. I will put out another example that corresponds to the lumped parameter version of a heat conduction model. We have already studied this. If you remember the heat exchanger model, okay? So for the lumped parameter version is basically the heat exchanger model. Remember, in the heat exchanger model, we had distinct components, and we defined all equations as component equations and topological equations. That means we defined the interface between two components, and we studied how heat was being transferred from one to the other. if there was a temperature difference between the two components, at the interface you had heat conduction, heat flow, that was linearly related with the temperature difference between the two components. Okay, so every equation that we have written was basically between components. So we defined the components of the system, and between each component we defined how heat was actually being transferred, and from that we obtained a heat exchanger model. This was a lumped parameter model, because we did not care about what was happening along distances. We did not care about what was happening within a component. We just assumed that it was equations of components and their interrelationships. Okay, that is the basic idea behind the lumped parameter version. If you think about the circuit, okay, you have capacitors, you have inductors, you have resistors. So and you have interconnection of those components. So everything is happening either within the interconnection, and every component had terminal equations. We never cared about what's happening within a resistor, for example, how the heat was dissipated or how heat was being propagated along a resistor and so on. Okay? So what's the difference of a distributed parameter system? In a distributed parameter system, the variables are not a function of time. Okay, so let's say a lumped parameter model, what we have is all variables are only a function of time. So for example, you have a capacitor voltage, it is Vc of t. Okay, we don't have any other variable involved. Okay, it's the capacitor voltage. We are not talking about the voltage across different regions of the capacitor. If we talk about the voltage of a resistor or the current through a resistor, we are not talking about the current through different locations, different parts of the resistor. It's only the resistor current, and it's a function of time. Now, when you have a distributed parameter model, now all variables are a function of time and some other variable. This can often be a space variable, but not necessarily. There can be other variables resulting in other interesting systems, but if it's a space variable, then what you're talking about is that you also worry about where you are measuring the variable. Okay, for example, if you are think about a transmission line, let's say, is going from Ankara to Istanbul. It's a very long cable. Now normally in terms of a lumped parameter approximation, it's a conductor. Therefore, in the lumped parameter approximation, there is only a single voltage across that conductor and ground. Okay? But when you introduce a distributed parameter model, what you are saying is that, okay, the voltage is not only a function of time, but it's also a function of where you measure the voltage. Okay? So, for example, in a transmission line, okay, a transmission line, you have a voltage, but a voltage is a function of time and x. So meaning that this is your x-axis, let's say. So, for example, at this point, you have VT0, the voltage on that cable at space variable being set to 0. So, at the voltage at Ankara output. And also you can talk about a voltage VT x1, let's say, assuming that this is x1. Okay, so this is, for example, the voltage at Istanbul output. Okay, so the conductor is not an ideal conductor anymore, but the whole system becomes a distributed parameter system. Okay, now distributed parameter systems are often approximated by higher order lumped parameter models. For example, this may be approximately equal to, for example, basically you can have a resistor and a capacitor, okay, and then another resistor and another capacitor, okay, and you can continue like that with a large number of resistors and capacitors. Okay, so instead of having a voltage that is a function of time and a function of space, instead you start having VT1 and VT2 and VT3 and up to VTN. So instead of having a continuously varying voltage across space, you can approximate that with a large number of lumped parameter variables. Okay, so that you have identical C's here, identical R's, and maybe even you may have non-identical variables as well for the model. Okay, this is an approximation. So what we will do is that we will first look at the mathematics behind not the approximation but the actual distributed parameter model. Okay, and then we will discuss how we can approximate that in order to build easy to handle models. But clearly we can see from this is that a distributed parameter model of very low order may become a lumped parameter model of very high order. Okay, because the approximation imposes a large number of variables and a large number of components in order to maintain the approximation. Okay. All right. So I'm gonna just sketch the heat conduction model, and then tomorrow we will start deriving that. Okay. But here is the model. Okay. By the way, note. Okay. Lumped parameter models. Result in ordinary differential equations. The kind that we have been dealing with in all our systems lectures. Unfortunately, distributed parameter models originally result in partial differential equations, which are much more difficult to deal with. Okay, differential equations. So originally, a distributed parameter model results in a partial differential equation, which can again be represented or approximated by an ordinary differential equation of much higher order. Okay. So here is the model that we will study. We will heat conduction in a solid body means we will consider a solid piece of heat conducting material, often a metal. Okay. So this is heat conducting body. We will assume insulators around so that heat cannot escape from the side boundaries to simplify the model. Okay, so this is going to be insulators. When we say insulator, obviously we are talking about a heat insulator because this is a heat system. And what we will assume is that this has an area of A, cross-sectional area, okay? And then what's going to happen is that heat will be coming in from one end. We will call this Q omega of 0. And heat will be coming out from the end. This is going to be Q omega at L. The length of this will be L. Okay? And we will consider essentially an element somewhere along this length. Let's call this at a distance x. Okay, so this is our x-axis. And we will also consider the inflow of heat here and outflow of heat. And this we will say QW at x and QW at x plus dx. Because this distance over here will be considered to be an infinitesimally small distance dx. Okay? And temperature along the rod will be Txt. Okay? A function of space, which is x, and time, which is t. So as we have discussed, what's going to happen is that the temperature will be different everywhere along this rod. It's going to be a function of time, so it will be every temperature at every location in this rod will be changing with time as a response to the incoming heat flow and an outgoing heat flow. And we want to know how this is behaving. We want to know the model of how this thing behaves. Okay? This is a distributed model because the voltage across this heat conducting body is a function of time and a function of space along that rod. Okay? Alright. Do you guys have any questions at this point? I'm going to finish at this point, and tomorrow we will pick up from here and continue. Soru var mı arkadaşlar? Peki. 430'da kolay gelsin. Quiz mi var dediniz? Sınav mı var demiştiniz?
402 midterm hocam.
Ha, 402 midterm'ü. Hadi bakalım. Başarılar arkadaşlar.
Teşekkürler hocam.
Görüşmek üzere. Yarın sabah görüşmek üzere arkadaşlar.
İyi günler hocam.
Görüşürüz.